Okay, everybody, welcome to class. I lost my voice because I have tiny, adorable germ factory children. So we have Freddy Krueger voice, fitting for the week. I'm going to have to use the microphone, though, because I'm not very loud. Couple things today. We're going to do the first half of chapter 6, but I do have some announcements. I'm going to be out of the country next week on Monday and Wednesday. So I have pre-recorded the lectures for those days. So the latter half of Diffusion, halfway down, I've already recorded it and notes are here. And they're already all messed up because I've added space. So I'm going to finish the lecture today and put it online. And then you can watch the other 2 lectures anytime you'd like. Instead of having them in class, which we've done in the past, you can come on Monday and Wednesday just for homework help and midterm review. Make sure to bring your homework in on Wednesday, right? You still do have to turn in your homework on Wednesday, but I don't care if you stay the whole class. There won't be clicker questions. Instead, the TAs are just going to do homework help all Monday and midterm review all Wednesday, okay? So watch the videos anytime you like. That said, I get back Wednesday night, and the test is Friday, which doesn't give me a bunch of time for a midterm review, so we can do one of 2 options. I can do the midterm review Wednesday night, but I won't be able to do it in person. I'll have to just make a video and do my best to go over the topics. That's one option. The other option is I come in on Thursday night and I can actually do face-to-face questions if you have specific ones. I guess a third option would be send me the questions ahead of time that you have, and I'll cover them on the Wednesday night thing. The benefit to the Wednesday night is I'll post it with 2 days in advance of the test. Thursday doesn't give you a lot of time because the test is the next day. So we'll do a quick poll. Would you prefer A or B? A would be an in-person review on Thursday night. B would be a video review of just all the study guide topics, which I'll have posted by Sunday. But that's going to be on Wednesday night, 2 nights before. So go ahead, get your answers in. There's no correct. It's just participation on this. What's up, Andrew? Good question. Danny, actually, do you know if we have set aside an evening midterm review session from the TAs or not?
We haven't, but we were thinking of just doing a review session in class on Wednesday when we all are able to come anyway, we do it in class usually, so that's also an option.
Yeah, maybe that's the current plan. If people think that they need more time or something, maybe send us an email and we can decide what might work. Okay, so I'm going to close this poll. All right, people definitely prefer the video review Wednesday night. Okay, that's easier. Then you don't have to come anyways. I think it's just easier for everyone. So I'll make a video in my garage or something. And it'll just cover to the best. But like I said, if you want specific things covered and you're not sure if I'm going to get to it, shoot me an email and I'll be sure to go over specific questions as well. That works for me. Okay. Yeah.
How do we know what chapters exactly you're going to be pinpointing?
So I will put the midterm study guide up, and that will make it clear. But just so you're all aware, this midterm will cover everything that wasn't on the last midterm. So the last midterm, we did crystal structure. We didn't do polymer structure on the last midterm. So chapters 4, 5, 7, 8, 6, and 17 are all technically fair game. But I can't write 7 questions. You're going to get 3 questions, right? And the study guide will make it very clear what to study for. It's going to make it so you can really focus on certain topics to study. And I've said it before, but it bears repeating. Every midterm is built out of a homework question that you've seen. So the best thing to study is previous homeworks, right? Look up the notes from class for sure, but the best thing to study is the previous homework that tags along to that question. Okay. That said, so our learning objectives, we will say a few words about the last chapter that we didn't get to. And in chapter 6, we're going to start talking about why on earth we care about diffusion. What is diffusion? We're going to describe how atomic motion works and how this governs the rate of atoms moving through a lattice. We're going to introduce the concept of an activation energy and a chemical potential and how that leads as driving forces and inhibitors for motion. And by the end of class, we're going to get to Fick's first law for mass transport. But before we do chapter 6, let's just do a quick recap of the very last things in chapter 8. The very last thing that we didn't quite have time to get to was stress relaxation in polymers. Stress relaxation in polymers, we showed you it briefly in a previous chapter, but it said that the stress that you apply on a polymer is going to slowly relax, and that's because the polymer chains can slide past one another. So the stress at any given time is right there. That's going to be a function of your initial stress, sigma naught, multiplied by the exponential of negative modulus, that's your stiffness, Young's modulus, times time divided by viscosity. Okay? So I think there's a question on the homework that you saw where you had to relate viscosity to, that's the viscosity at the glassy transition temperature, 10 to the 12 Pascal seconds. And we found a way to modify it at different temperatures. And it was something like negative 17.4 temperature minus the glassy transition temperature. And then the bottom was, I don't remember, 51.6, I think. Right here. 51.6 plus T minus TG. So if you did need to know what the viscosity was at a different temperature, this would be the equation that you could use as a first approximation. The problem with this, what's called the WLF equation for viscosity, is that you need to know what these constants are and they're material dependent. So if you just use 17.4 and 51.6 for all the materials, it's not going to get it right all the time. It's just an approximation. Okay? Let's do a quick calculation though with this. Let's assume the following. It says, at the glassy transition temperature, you observe a stress of 100 megapascals produces 10% strain. What does this stress decay to after 2 minutes? Give the answer in megapascals with 1 decimal place. And if you don't know where to start or if you want a hand, we've got a couple TAs that can help out. Just raise your hand. Sorry, scoot past you. Okay, how can I help?
We don't have temperature, glassy temperature.
Well, you're told that you're at the glassy transition temperature. So that tells you what the viscosity is, right?
Oh, it's 10 to the 12. I do remember. 10 to the 12 Pascal
Yeah,
seconds.
yep. Other questions I can answer? That's in, well, if you notice that viscosity is in Pascal seconds, T has to be in seconds to cancel out. So if you keep your units, you'll get it right eventually, but just put it in seconds. Okay, another minute or two, we're going to close the poll. Did I? Oh, I do. No luck? Hey, let me start and stop and restart it. How about now? Any luck? Oh, there it goes. Sorry. Obscene. I leave Friday afternoon, and I don't arrive until Saturday night. But, like, you go forward in time 8 hours. It's something like a day of travel. It's awful. What's up?
How to relate stress and strain.
Oh, Hooke's law. Remember, stress equals Young's modulus times strain. So stress is equal to E times epsilon. Okay, maybe one more minute. We're going to close this poll. Okay, go ahead, get your answers in. Get something in. Get half your points. We're going to go ahead and wrap this up, closing it now. Okay, here goes. Okay, what did people think? Hey, there's some consensus around 21 or 11. Well, let's see what we got. Let's see what we got. All right. So to do this question, we need modulus. So remember Hooke's law to get modulus. So if we need to solve for big E, it's just going to be the stress divided by that strain. The stress was given in 10% strain, so turn that into not a percent when you solve for the modulus, right? That is in megapascals, but viscosity is reported in Pascal seconds. So to make our life easier, let's just convert it to pascals right now. So that's going to be 100 times 10 to the 6th pascals. Multiply that by time. Which is 2 minutes. Let's put that in seconds because viscosity is in Pascal seconds. So that's going to be 120 seconds. And divide this by 10 to the 12th Pascal seconds. So we stated that this happened at the glassy transition temperature. And by definition, the glassy transition temperature is when the viscosity is 10 to the 12th Pascal seconds. So that's something you want to put on your equation sheet. I didn't bring my calculator. Somebody punch this in for us and see what you get. There are. Oh, sorry. There's also a negative sign I missed. Don't forget that negative sign or it won't work. Okay, I get 88.7. Anybody else getting 88.7 megapascals? I'm guessing the vast majority of mistakes on this had to do with either not remembering what the glassy transition temperature viscosity was, using wrong units, or forgetting maybe Hooke's law, right? But this is a pretty straightforward calculation in terms of time. It's not too hard. It's just remembering those key things. All right, let's say a few more things about molecular weight. As you increase the molecular weight, the modulus doesn't change that much, but the tensile strength does change. As you go towards longer and longer molecular weight chains, there's more and more overlap, so the bonding gets stronger, which makes sense why the tensile strength increases. Degree of crystallinity, let's see, this changes. A secondary bonding prevalent in crystalline regions where the chains are oriented with one another. So if you have a more crystalline polymer, then you have more fraction that's bonded together, even with van der Waals bonding. So that will increase your modulus, okay? Modulus will increase with crystallinity, and obviously tensile strength will as well. Okay, those are the last things on Chapter 8. Any last questions on deformation mechanisms, on mechanical properties? Because I think we're going to move on to diffusion now. Yeah, Becca? Oh, thank you. Okay. The units in the exponential cancel out, and the unit in the pre-exponential was megapascals, so it is megapascals. Good, good thing about it, though. All right, so let's move on to Chapter 6, which is diffusion. Okay? So diffusion is another important engineering process. You can't help but use it. We use it all the time. So this gun up there that has that sort of patina look to it on that casing, that's something called case hardening. They do it intentionally. And all they do is you start out with the steel, and then you expose it to either nitrogen or carbon. And over a while, that nitrogen or carbon will diffuse into the steel. And the reason that they do that is by putting carbon and nitrogen into the lattice, you start to fill what are called the interstitial sites. If you remember back to crystal structure, interstitial sites are the ones between the atoms. And so by putting atoms in those spots, you make it harder for slip of dislocations. Therefore, you made it harder. And you made it harder right at the surface, so you made it less prone to be scratched. So it's a way to not only make it look kind of nice, but you prevent scratching when you do case hardening. And they do this in all sorts of stuff. Take these different materials here. I don't know what exactly these are, but they're adding carbon to the outside. And as they change the conditions of the heat treatment, the carbon is changing how far it can travel into the material, right? You can see that just by the color. You got this thick ring here, but in the other ones it's thinner and thinner. So an understanding of diffusion will help us understand how far into materials diffusion will occur, right? So we've got a cool demo for this. It's the most dangerous one to date, and I need a volunteer. But like, you have to be really sure. Are you sure, Ashton? Okay, come on down. Okay. Ashton, I hope you don't mind smelling like dark temptation axe. Because you're about to. But for science. He's risking life and limb for science, for all of us to learn. So, I'm going to go ahead and spray him with this dark temptation axe body spray. And when you smell it, I'd like you to raise your hand. No one smells it? You guys don't smell it yet? I wait for it. It's coming. Oh, gosh. I have to get on a plane later today. I'm going to smell so dark and tempting. Hands up. You smell it? We're like running out of juice over here. Holy crap. How do you not smell that? You're a good sport, Ashton. Okay. This may be the longest I've ever done this demo. Alright, we're going to call it. Thank you, Ashton. Wait, before you go, because now you smell so strongly, you have your option of a small, medium, or a large Sparks Research Group shirt, which of course has a crystal structure on it, because we're not barbarians. You want a medium? There you go. That's you.
Thank you.
All right. Hey, let's give Ashton a hand. Okay, so the principle that demo is to illustrate is that, first off, the gas moving through this room, it moved like meters. It moved huge distances, and the reason why it was able to do so is something called convection, right? Convection in the air. That means currents of air, big swaths of molecules, are moving together. That's different than diffusion. But there is one thing that's similar to diffusion. It's similar in that if you have a concentrated region of a type of molecule over here, that molecule is going to travel down the concentration gradient. That's why if you saw the hands in the room, we smelt it really quickly because we were I'm like doused in it. Ashton's really doused in it, right? And it sort of spread its way through the room, okay? So let's tie this back to material science. We learned about the eutectic structure. And the eutectic structure, we said if you cool it down right here at the eutectic point, the type of microstructure that you get looks like these sort of zebra stripes. And we said the reason that that forms is that you go from a liquid to a solid. And it happens very, very quickly at a single temperature, essentially. The liquid was a mixture of the two different phases. But if you look at the phase diagram, in this region, it's a two-phase region. And your elements are basically pure gold and pure silicon. So what used to be a nice mixture of atoms almost instantly has to separate into pure gold and pure silicon. That means atoms have to diffuse and separate from one another. And if this happens at a low temperature, like this does at, 200, I don't know, some low, 500 degrees, then it doesn't have the time and the mobility to separate very far. And that's why you see these tiger stripes. These represent phase boundaries. These are grain boundaries, right? Grain boundaries cost energy. The system would like to get rid of these, but it just can't do it because diffusion is too slow. Moving all these atoms to get a big black glob and a big white glob would just take more mobility than these atoms have. Okay? So when we start talking about diffusion, one of the first things we can do is we can build what's called a diffusion couple, right? A diffusion couple means, let's say I take a copper bar and a nickel bar. So I've got copper and I've got nickel. And I weld them together, right? I bond them together, I weld them, I press them together. And then I heat treat them. What will happen when I heat treat them, right? After a very long time. This is our next clicker question, I think. Okay, if I weld a copper and a nickel bar together, and I heat them up for an infinitely long time, what will happen? A, nothing. B, you get a mixing of the atoms, but you end up with a copper-rich and a nickel-rich region. Or C, a completely homogeneous mixture. And we've already said that things go down the concentration gradient, so it would make sense that there's some mixing maybe, but the real question is B versus C, right? Do you always have a nickel-rich and a copper-rich, or is it completely mixed? Okay, get your answers in. Yeah, it's so strong. Easily the longest we've ever done that demo. I need my wife to bring me like another shirt for the airplane. Everything okay? Okay, get your answers in. We're going to close the poll. Okay, people think, yeah. The key word here is that we held it an infinitely long time. Infinitely means that given long enough, as long as there's a concentration gradient, meaning it's more rich in copper, less rich in copper, copper atoms are going to keep on moving that direction. So infinitely long, it will be completely evenly mixed. What about in times less than infinity? In times less than infinity, you're going to see a concentration profile, right? So if we were to draw the concentration of copper, after a while it might look something like this. Whereas the concentration of nickel might look like this. They do not have to be symmetrical. That's an important point. They do not have to be symmetrical. In fact, the only time that they are symmetrical, that means that the diffusion rate, right, or what we're going to get to is called the diffusion coefficient, is equal for each species in each host. So the species is the atom that's diffusing, and the host is the lattice it's diffusing into. If those are the same for copper into nickel as it is for nickel into copper, then you'll get a symmetric profile, but it doesn't have to be that way. Okay? So there's here's an interesting way to think about diffusion. Somebody made a nice cartoon for it. Somewhere here. There it is. So here they're showing atoms at the interstitial positions of the blue lattice. And then they give these things atomic vibrations, right? And you see that on average, these white atoms are starting to spread out. there was a whole bunch of empty space on the right-hand side, and they were concentrated on the left-hand side. So it was a higher concentration, lower concentration. And if these things move randomly, they can't move into a spot that's already occupied, so their average flux is going to be to the right. A flux simply means that there's an amount of something moving per area per time. Okay? So that's sort of an atomistic interpretation of diffusion. We can actually turn that into a nice cartoon, right? So let's go ahead and draw an axis here. We're going to draw energy versus distance in our lattice, right? Let's give ourselves an axis like this. So that's in the x direction. We're going to draw energy up here, right? So when an atom starts out, let's say that we want to hop from one spot to another. Typically what happens in terms of energy is that when it's in its spot where it started out, that's a spot that's lower energy. And as it hops to another spot, it has to overcome an energy barrier, right? So the plot might look something like this, right? This is where the atom started out at some lower energy. And when it moves a distance over to this point, we're going to call that distance lambda. That's the distance between hopping sites. It typically has to overcome some energy barrier, right? So this energy barrier, we're going to give it a name. We're going to call it the activation energy, delta G M. That's an activation energy from going from one site to the other. And maybe the right way to think of it is that if you're an atom that's going to move over here, you have to break bonds, you have to squeeze other atoms out of the way. So it makes sense that in that transition period, as you're moving to an empty seat, that you're going to have to cost a little bit of energy. But once you get there, you're going to gain some energy because you're going to form new bonds. The strained atoms go back to normal. So that's this difference in energy, right? So that's our activation energy for jumping, and that's our jump distance. Let's modify this now, right? Let's assume that you can hop in both directions. So we're going to draw our axes. So you've got energy. This goes from site 1 to site 2, right? So you've got, your curve looks like this. Okay? So we could figure out what's the rate of atoms moving from the left to the right, from 1 to 2. We could also calculate the rate from going 2 to 1, right? So we could calculate dN1 dt. That's the change in N. N is the concentration. So the change in concentration with respect to time on site 1. And we could figure out the change in concentration of site 2 with respect to time. Okay? So we have concentration N1 over here, concentration N2 over there. We have our same activation energy as before. And in this case, with no driving force, then the rate of change of atoms from site 1 to site 2 versus site 2 to site 1 is going to be the same. They both overcome the same activation energy, right? So we're going to say that dN1 dt equals dN2 dt, and that equals this expression, V times F. V is the attempt frequency. So if an atom's vibrating, each time it's vibrating, that's an attempt. Like as it jumps from side to side, one of those times it might actually jump over to the other side, right? That's V. F is the fraction of atoms in the correct configuration. What do I mean by that? If we go back to this drawing, for this white atom to keep on hopping that way, this has to be an empty spot next to it. Like, this guy can't jump up because there was an atom above him. So that's not right. Also, it takes into account what's the direction, because we define the direction from 1 to 2. So only one of its 6 directions it can jump is in the right direction. That makes sense? So it's just a fraction that accounts for geometry. Then you've got an exponential of your activation energy. This is a thermally activated process, so you have thermal energy in the bottom. We're going to call that whole thing gamma. Okay? This is just some background for diffusion. We use simpler equations in this chapter, so don't sweat these equations I'm going through right now. This is just background. Okay? We're going to modify this now. We said when there's no diffusion gradient that the rate of atoms hopping from one site to the other is the same as them hopping right back. So there's no net flux. There's no movement through some area per unit time. But if we apply a gradient in the concentration, or what we call the chemical potential, then we do produce a net flux. Here's how it looks. So we're going to start with our axes just like before. This time going from site 1 to site 2, we're going to apply a gradient in the concentration. So the atoms at site 1 are much more concentrated, right? That makes it look like this. Okay? So right here, N1, N2. N1 is greater than N2. It's more concentrated. That changes the energy that we're at. It starts out at a higher energy level than N2 does, right? So therefore, we could figure out the rate of atoms moving from 1 to 2, and we could also figure out the rate of atoms going back from 2 to 1. But look at the energy barrier this time. There's like this massive difference. Atom going from 1 to 2 has our old friend delta GM, the same activation energy from before. But going from 2 to 1 has to overcome that plus this value right here, which we're going to label it as, what do I call my notes? We call that delta mu, where mu is the chemical potential. So it's the change in the chemical potential. That's equal to lambda, or jump distance, multiplied by the gradient in the chemical potential. What is the chemical potential? We briefly talked about it in chapter 10. Doesn't matter if you don't understand it well in this class. All it is it's a measure of how much the energy changes in a system when you add or remove an atom. So that's exactly the metric we want here, because we are removing an atom. So we want to know how much does the energy change on that y-axis every time I pull an atom out, right? So if you have a big difference in chemical potential, which comes from a difference in your concentrations, then you see a really big driving force to go from 1 to 2, but only a small driving force to go back, right? There's a bigger barrier going backwards. Therefore, the forward jump from 1 to 2 is favorable, right? We can calculate what the expression is from 1 to 2. It's the same as before, VF, exponential of our activation energy. But going backwards has this extra term in the activation energy. And since that's in an exponential, it basically it makes it very hard for it to jump uphill, up the concentration gradient. Nevertheless, we could subtract the two to figure out our net transport, and you get a more complicated expression. If the chemical potential is small, that simplifies to this value. Gamma times our change in our chemical potential divided by thermal energy. So finally, we can introduce flux now. Flux is important. Flux is number or amount of atoms per area per time. So for example, if you're trying to measure the flux of water in a river, you could take a square meter of that river, and if you could calculate how many molecules of water go through it per area per time, that would be the flux of your river, right? So that's different than the total amount of water in the river. This is measuring, in some cross-sectional area, what's the flow of matter going through that area. So in physics, you probably learned about flux with electrical current density, right? The current density is the flux of electrons traveling through something per unit area, per unit time. Or maybe magnetic field. You would have seen this in physics at some point. Okay? So, so J is our flux. J is usually the variable for a flux. It's going to be equal to 1/6. 1/6 comes from the geometric that if we're talking about movement in that direction, of the 6 ways that I can go, up, down, forward, backwards, left, or right, only one of those 6 moves me in the direction that I've defined, right? So that's the 1/6. You've got C times lambda times gamma. Gamma we defined up here. Lambda is the jump distance. C, I'm forgetting offhand what that is. And then you've got your difference in chemical potential divided by thermal energy, right? So technically speaking, you can come up with a first principle, meaning all based off of atomic interactions, what should be the flux of atomic motion. We're not going to use that in this class. If you take another transport class later on in your college career, which most of you will, you'll see more of that. In this class, we're going to keep it simple, and we're going to do a proxy for this. This expression, which has flux equal to a bunch of stuff multiplied by the difference in your chemical potential, can really be thought of as the following. This right here, oops, that guy is your driving force. Whereas the other part right here, this is a constant of proportionality. And then on the left-hand side, you've got your flux. In other words, every time in science, if you ever see a flux, it is always defined the same way. Flux is always equal to a driving force multiplied by some constant of proportionality. Whether that's electrical current density, which we'll talk about later in this class, or mass or heat, there's always a driving force. In this case, the driving force is the concentration gradient. So high concentration, low gradient, that's our driving force. There's a bunch of stuff that's going to turn into a constant of proportionality, and then you got your flux. Okay? So there's different mechanisms that things can happen to get motion. Different diffusion mechanisms. So atomic motion depends on a couple of conditions. First off, the adjacent site, if I'm talking about flux from one side to the other, the adjacent seat needs to be empty. So for Hector to move from this site to that seat, this seat needs to be empty. That condition needs to be met, right? What else? The atom has to have sufficient energy to break the bonds with its current neighbors, to distort the lattice as it moves, right? That's all the activation energy. So if you're at a low temperature, right? Imagine that he was bonded to other atoms here, right? If he wants to move to there, he has to first break the bonds that he's already with, and then he has to squeeze past the lattice and sit down again, right? So that activation energy, if you don't have that thermal energy to overcome that activation energy, then you're not going to be able to diffuse. That's why temperature is such a big deal with diffusion. If you add thermal energy, you can overcome that activation energy, okay? Now, when we say thermal energy, it's wrong to think that all the atoms are vibrating at the same frequency. Not the same frequency, but the same amplitude. There's an average amplitude that they're vibrating at. There's an average energy, but there's always outliers. Like, it's always a distribution, just like we saw with Weibull statistics. When you look at energy of atoms versus number of atoms, it's always going to be something like this, right? So there's an average energy that they're vibrating at. I drew that the wrong way. That's the wrong axis, but still. Some of them will have high enough energy to diffuse, even at low temperatures. But the higher and higher the temperature you take it, a higher fraction of your atoms will be able to diffuse because they're over that activation energy. Okay? All right, there's two mechanisms for diffusion. There's vacancy diffusion and interstitial diffusion. Vacancy diffusion relies on hopping from lattice sites that are empty. So in this example here, if these guys at the far end of this row want to diffuse that way, this vacancy diffuses that way. Students move this way, the vacancy moves that way, right? Avery would sit here, the vacancy moved over. I forgot your name. Ryan would sit in the vacancy, it moved over again, and so on down the line to Connor and to, I forgot your name. Matt, right? So atomic motion and vacancy motion are in opposite directions in the vacancy mechanism. But there's another way to do it, right? What if instead of hopping from seat to seat, what if it's a really small atom? Then I could go down this aisle between students, right? If it's a small atom like a carbon or a nitrogen or a hydrogen, right? These things can leave the atoms present. They don't have to take their seats. They can sort of squeeze past them. This only works for small atoms. It doesn't work for big ones, okay? So the question is, which one's faster, right? This is our next clicker question, I think. Which mechanism will be faster, vacancy diffusion or interstitial diffusion? Some horrible creepy, yeah, the dark temptation. I don't blame you, Spider. Okay, get your answers in. We're going to close the poll. Vacancy versus interstitial. Okay, we're going to close the poll. Okay. People think what? People think interstitial, yeah. So, for a couple reasons. Why is interstitial faster? What do you guys think? Who voted interstitial, and what's your rationale? What do you think, Ashton?
Interstitial, because there aren't chemical bonds between that molecule that bonds around them, so they don't have to break these much stronger bonds than a vacancy that will break them around and move over.
That's not what I've thought of before. I think that's generally true. If you take steel and you put carbon into it, the iron is still mostly bonded to iron, although it might start bonding with the carbon as it's sitting interstitially. But I generally think that's a true statement, that there's weaker bonds that it has to overcome. What do you think?
I kind of thought that just like in traffic, like
Absolutely. Which is why I'm so sad that we didn't. This like 2 years ago came up in the Utah legislature and they said no to it for white lining. That's exactly right. And that really means that you don't have to wait for a vacancy because interstitials, by definition, an interstitial is a site that's not occupied. So if you're hopping in those unoccupied sites, the odds of it being empty in front of you is really good. So that's two good reasons we've heard. There's a third one. Any other reason why interstitial tends to be faster? Did I step on it? A horrible creature. What other reason is there? It has to do with that one that you just said. Interstitials tend to be smaller atoms moving. Smaller atoms tend to distort the lattice less, right? So small atoms just tend to move faster because they don't distort things as much. That's why interstitial is faster. Okay. Okay, this brings us to the final big topic we're going to talk about today is Fick's first law. So when we talk about diffusion, ultimately we're engineers. What we really want is I want you to be able to tell me for a given temperature and time or something, how far are things going to diffuse into my material? Or maybe how much flux, how much movement of atoms per area per time am I going to see through my material, right? And to do that, we need two different scenarios. One is Fick's first law, and then there's Fick's second law. Fick's first law has to do with what's called steady state diffusion. Steady state diffusion means that the rate of diffusion is not changing with respect to time. Okay? The rate, or better said, the rate of flux is constant. So in other words, if there's a river that's flowing and the flow of water in that river is constant, then the flux per unit area per unit time isn't changing. We could use steady state conditions there, right? But what about during a rainstorm? In a rainstorm, like a flash flood, the flow of that river is changing pretty rapidly with respect to time. So we can't use an expression that doesn't have time in it because we have to account for that change with respect to time. So the easier one is steady state because it's time independent. It's the rate of diffusion's not changing, right? And in that case, we have the following law. J, our flux of atoms, is equal to negative d, the diffusion coefficient, multiplied by dc dx. dc, that's the change in the concentration over dx, right? So it's your gradient in your concentration multiplied by the diffusion coefficient, okay? And let's go ahead and figure out what should the units be of this, right? If we do a unit analysis on this, the left-hand side is a flux, and we've already said a couple times that flux is always defined as the amount of something per area per time. So let's do moles per centimeter squared per second, right? Now dc dx, that's the change in concentration, so that's going to be moles per centimeter cubed, divided by distance, right? So what should be the units of the diffusion coefficient? Maybe turn to a neighbor and work out what should be the units of our diffusion coefficient. Okay, what should the units be? It's at the bottom of the screen. Oh, sorry. That's wrong. Centimeters. dc dx, right? Concentration is the amount per volume. So that's concentration, dc. And then x is just a length. So what should be the units of our diffusion coefficient? All right, Connor, you're explaining it correctly. You want to explain it to everybody?
Sure. So it's centimeters squared over seconds, because that centimeter goes up and makes centimeters to the power of 4.
Yep.
A squared centimeters on top, make that go squared, and a seconds on bottom.
Yep, that's exactly right. Centimeter cubed divided by centimeter goes to centimeter to the fourth. So if we want centimeter squared over here, you have to have a centimeter squared up in the numerator and then a per second. So that's going to be the units, right, of our diffusion coefficient. Now, we define this with a negative sign because we're going to say that in mass transport, as in thermal transport, things go down the concentration gradient. That's where the negative sign comes from. So we're moving down the concentration gradient, okay? The last thing I'll talk about is some factors that influence diffusion and how to plot it. So the diffusion coefficient can be calculated for any species at any temperature by this expression. D, the diffusion coefficient for some species at some temperature, is equal to a pre-exponential, D naught, multiplied by the exponential of negative QD, that's going to be the activation energy for diffusion, right, divided by RT. If you're dividing it by RT, that means that you're working with moles of atoms, right? So this would be a diffusion on, if the energy would need to be energy per mole of diffusing species, it's just as common to talk about on a per atom species. If it's a per atom species, then that needs to be kBT, Boltzmann constant times temperature, right? Those things are related just by the number of moles, okay? Because of that, you could actually take natural log of both sides of this, and you could make it look linear. We've seen this like a million times this semester. So if you thought like, oh, I don't have to learn it because like, it'll just be this one time, like it just keeps coming back. You can make one of these Arrhenius equations look linear if you plot it in the right way. If you plot the diffusion coefficient with a log plot, or if you take natural log of the actual values, and you put that against 1 over temperature, 1 over temperature is your x value, this is all y, your slope will be your activation energy divided by r, right? So if I gave you this plot on a test, or on a homework, you could figure out, I could say, what's the activation energy for diffusion? It's pretty straightforward. You say, well, that's the slope. And I know that the slope for these materials is equal to the rise over the run. And what I'm talking about is natural log of D2 minus the natural log of D1 over x2 minus x1. That will equal negative Q over R. R is just the gas constant. So you can solve for Q. Okay? So giving you a plot like that would be fair game on a midterm or on a homework. Okay? What's great about this is that for anything you can figure out the diffusion coefficient because every different setup, some diffusing species and some host lattice, will have a different D naught and a different activation energy. So if I give you the activation energy and the D naught value, you can tell me what's the diffusion coefficient at any temperature just by plugging in T. Okay? So the last thing, which we won't have time to do today, but you could imagine like copper dissolving, or copper diffusing in zinc, or zinc diffusing in copper. If I gave you the D naught values for these and the Q values for those, I could ask you to tell me the temperature at which they would be the same. And to solve that, you would simply do, okay, D naught for copper in zinc multiplied by the exponential of negative activation energy for copper in zinc over RT. And you would set that equal to D naught for zinc and copper multiplied by the exponential of negative QD for zinc all over RT. And you'd ask yourself, is there one temperature that satisfies this equation? If so, then there's a temperature when these things diffuse at the same rate. Okay, that's it. So again, I will be gone Monday and Wednesday. Come to class if you want help. Make sure you turn in your homework on Wednesday. And otherwise, we'll see you a week from today on the exam.